Welcome to this explainer. Today, we're totally demystifying the merge sort algorithm. We'll be taking it from a super high-level concept all the way down to concrete pseudocode. So, let's just dive right in.
To keep things organized, we're breaking this down into 5 quick stages. First, the need for speed. Then, phase 1, the divide. Phase 2, the merge. After that, we'll hit the recursive pseudocode. And finally, time and space complexity.
All right, part 1. The need for speed, escaping O of n squared.
You know, it's completely natural to wonder why we're adding yet another tool to our coding toolbox when our standard sorting methods already get the job done, right? If you've studied algorithms, you've likely spent plenty of time mastering bubble, insertion, and selection sorts. So why do we even need another one?
Well, the stark contrast here is sheer speed. While those early algorithms drag at an n-squared pace, meaning as your data grows, the computation time grows exponentially, basically leaving you staring at a loading bar forever. This new approach slashes that time dramatically, down to O of n log n. This kind of optimization is absolutely crucial when dealing with massive arrays. You simply cannot rely on n-squared algorithms for real-world data scales. It's a real game changer.
Okay, moving on to part 2. Phase 1, divide.
Listen, every time you feel like you're getting lost in the weeds of this algorithm, I want you to anchor right back to this core mantra. It's fundamentally driven by just 2 continuous, repeated actions. We divide, and then we merge. That's the whole shebang.
And right here is the biggest aha moment of the entire concept. We aren't eating up memory by actually tearing arrays apart and spinning up entirely new subarrays. No way. We're merely pointing to different sections of the original array hypothetically. We do this by utilizing low, mid, and high indices to track our boundaries.
Let's map out exactly how this works. Say we have an array of 9 elements, an odd number, right? We split it, hypothetically, into 5 and 4. Then we continually break those subsections down. The 5 elements split into 3 and 2. The 3 splits into 2 and 1. We just keep going until we hit rock bottom with single, indivisible elements. And why stop there? Well, because a single element, standing completely all by itself, is automatically already sorted.
Which brings us to part 3, phase 2, merge.
Now we take those hypothetical sorted arrays, establish 2 pointers, and constantly ask ourselves, okay, which number is smaller to go into our temporary array next? So if our left array element is a 1 and our right array element is a 2, the 1 obviously wins. It gets placed into the temporary array and that specific pointer just shifts forward 1 spot. The merging logic here is beautifully simple. Really, just 4 steps. Compare the left and right pointers, pick the smaller element, and step the chosen pointer forward. But the real magic happens at step 4. If one array gets exhausted completely, meaning you've successfully placed all its elements into the temporary array, you don't need to do any more comparisons. You just blindly dump the rest of the surviving array right into the mix because it's already perfectly sorted.
All right, let's look at part 4, the recursive pseudocode.
As you can see mapped out here, our visual left array is simply dictated in the code by looking at the index range from low to mid. Meanwhile, the right array handles the index boundaries from mid plus 1 to high. I want to reiterate, we are strictly playing with pointers on the exact same original data structure.
But before we can recurse, we have to build our foundation with a base case to actually stop the loop. If low is greater than or equal to high, we simply return, because that tells us only a single element remains. Following that, we use a super simple math operation to find our dividing midpoint. Mid just equals low plus high divided by 2.
And here it is, the actual recursive engine of the pseudocode in action. Just 3 continuous steps. Tell the left half to sort itself from low to mid. Then tell the right half to sort itself from mid plus 1 to high. And finally, when those return, merge the 2 halves back together. Actually, it operates beautifully as a depth-first traversal, literally digging all the way down the left side before ever even touching the right.
Finally, we've made it to part 5, time and space complexity. The overarching time complexity for this algorithm proudly stands at big O of n log n. This is pretty much the gold standard for general-purpose sorting, but let's take a second to demystify exactly where that number comes from.
If you follow this timeline, because we divide our array in half at every single step, a 16-element array breaks down to 8, then 4, then 2, and finally 1. Notice it takes exactly 4 steps to break down to single units. This perfectly represents the mathematical log base 2 of n. I mean, 2 to the power of 4 is 16, right? And since the merging process at each of those levels takes n operations, we combine them to arrive at a really beautiful n log n total time complexity.
However, there is a bit of a trade-off here. Our space complexity sits at big O of n, precisely because of that temporary array we have to borrow during the merging process. We do need a separate structure to place the compared elements into before copying them back to the original array in their sorted order. But honestly, it's a relatively small memory footprint sacrifice for an absolutely massive gain in processing speed.
Which leaves us with a rather profound thought to wrap up this explainer. If a massive bottleneck like sorting can be conquered simply by breaking the data down into hypothetical halves, what other programming challenges can you solve with divide and merge? Once you really grasp this pattern, where else in your coding journey can you apply this identical, elegant strategy? Think about that as you go implement this into your own code.